How does Clausius inequality explain entropy in thermodynamics? Have you ever wondered how heat and energy interact in our universe? Today, we will break down a fascinating concept in thermodynamics known as the Clausius inequality and its role in explaining entropy. The Clausius inequality is a key part of the second law of thermodynamics. This law tells us that energy transformations are not always perfect and that some energy is lost as heat. The inequality provides a mathematical way to express this idea. It states that for any cyclic process, the integral of the heat transfer divided by the temperature of the reservoir is less than or equal to 0. In simpler terms, when we look at a system exchanging heat, we can calculate how much entropy is involved. Entropy is a measure of disorder or randomness in a system. According to the Clausius inequality, when a system absorbs heat from a reservoir, the change in entropy is at least equal to the heat absorbed divided by the temperature of that reservoir. For reversible processes, we can calculate this change exactly. However, in irreversible processes, which are more common in real life, the change in entropy is always greater. This is due to additional entropy created by factors like friction or heat transfer across temperature differences. From a mechanical engineering viewpoint, the Clausius inequality is essential for understanding how energy systems work. Engineers use this principle to analyze engines, refrigerators, and heat exchangers. For instance, when designing a heat engine, the Clausius inequality helps explain why no engine can achieve 100% efficiency. Some entropy is always produced, which reflects the unavoidable losses in any real process. One practical tool engineers use is the temperature-entropy diagram. This diagram plots temperature against entropy, helping visualize heat transfer processes. It allows engineers to calculate work and heat interactions in reversible cycles, which is vital for optimizing mechanical systems. In essence, the Clausius inequality illustrates that the total change in entropy for any real process is always non-negative. It connects heat transfer and temperature to changes in entropy, giving us a way to distinguish between reversible and irreversible processes. This understanding is crucial for mechanical engineers aiming to analyze and improve thermodynamic systems.